Today we're going to look at infinite power towers, and we're not going to find values of any specific infinite power towers. We're going to answer the question, when does this infinite power tower make sense? So we've got x to the x to the x to the x forever and ever and ever. And we want to find the values of x that make this object well defined. Now we could write this more carefully as follows. So let's define this tetration symbol. So we've got this x, well, to the n on the left-hand side. So that's the nth tetration of x, to be x to the x to the x n times, where we've got n total x's. And then our goal, our careful goal here, is to find the interval of convergence of the limit as n goes to infinity of this nth tetration of x. Okay, so let's start off with some exploration. Let's suppose that this object converges. So I'm just gonna maybe, since we're exploring, we can do this not super carefully. We're gonna say that this x to the x to the x to the x, so on and so forth, is equal to t. But now let's observe that this object has itself built inside. Notice that here we have t, because that's another infinite copy of powers of x. So that means that this is equivalent to saying that x to the t is equal to t. But observe, that's equivalent to, after taking the log base t of both sides, t log base t of x is equal to 1. So I just took the log base t of both sides. But now that's equivalent to saying that the log base t of x is equal to 1 over t, or more carefully, x is equal to, let's see, t to the power 1 over t. In other words, this kind of object makes sense if it's the image of this function t to the 1 over t. So that motivates us to look at that function for just a second. So let's say that this function, we're going to call it g of t, which is t to the 1 over t. Now, I'd like to get maybe a good picture of what the graph of this looks like. So I'm going to take the derivative to find a maximum or a minimum. But I need to use logarithmic differentiation here because I've got this goofy exponential type function. So let's observe that taking the log of both sides, I have the log of g is equal to 1 over t times the natural log of t. But that tells me that g prime of t over g of t, well, that's going to be 1 minus the log of t over t squared, just using the product rule. That's pretty straightforward. But now let's observe that g prime of t equals 0 if and only if we have the log of t equals 1. That numerator has to be equal to 0. But now that's equivalent to saying that t is equal to e. So that means we can get a pretty good picture of this function. So I'm going to maybe sketch it right here. So notice that it doesn't make sense if we're in the values of t which are negative. This function isn't defined there. But here, I'm going to sketch this out, and we're not going to do all of the details for these calculations, but I think they're pretty straightforward. So let's put here this number e. Now what happens is that we get an increasing function up to this value e, and the maximum is in fact equal to e to the 1 over e, just from plugging that in. And furthermore, if you take the limit as t goes to 0 from above, you'll get 0 here. So it's not actually super well defined here, so we could put an open circle there at the origin. And I'll leave it to you to take that limit if you want to. And then you might say, well, what happens in the infinite limit in the other direction? Well, that's not too hard to calculate. The infinite direction to the infinite limit to the right is in fact equal to 1. So let's put a horizontal asymptote there at 1. And this thing does something like that in that direction. So in my mind, that gives us a couple of obvious choices for possible values of x. Remember that x has to be in the form t to the 1 over t, so it has to be the output of this function, or one of the outputs of this function. So x could be any output of this function, so that would be maybe our first possibility. So I'll just put x is on the interval from 0 to e to the 1 over e, not including 0. It could be the values of the function that occur to the right of e. So that would be x is on the interval from 1 to e to the 1 over e. But notice here we can include 1 because this pretty clearly converges when x is equal to 1. Or it could be something goofier. So we could have x on the interval from a to e to the 1 over e, where a is some number between 0 and 1. So I'd like to maybe point out that those first two possibilities are the most intuitive. They can be guessed just from the picture of this graph, keeping in mind that the x values that we need are outputs of this graph. The third one is maybe like a worst case scenario. If one of the two obvious possibilities don't work, then there's got to be some number between 0 and 1 that can serve as that lower bound. Okay, so now let's continue our exploration to determine which of those possibilities is the actual value of the interval of convergence for our infinite tetration. Okay, so let's recall that we just motivated the following candidate intervals of convergence for our infinite tetration. We could have the x values on the half open interval from 0 to e to the 1 over e, on the closed interval from 1 to e to the 1 over e, or on the half open or closed interval from a to e to the 1 over e, where a is somewhere between 0 and 1. And the last one is like a worst case scenario if something breaks somewhere between 0 and 1. Okay, so let's look at this interval in the middle. Notice that that is the most restrictive interval. The two other intervals contain that as a subinterval. So let's just make sure that we do have convergence on the interval from 1 to e to the 1 over e. Okay, so let's suppose that x is on that interval 1 to e to the 1 over e like that. But then let's observe we clearly have an increasing sequence. So I'll just say have an increasing sequence that goes x is less than x to the x, which is less than x to the x to the x, which is less than x to the x to the x to the x, and so on and so forth. So we've got a monotonic sequence. Now we want to show that this sequence is bounded, and it's not actually so hard to show that it's bounded, so let's see how that might go. And then, of course, if we have a monotone sequence that's bounded above, then by the monotone sequence theorem, this thing converges. Okay, so let's observe that x is less than or equal to e to the 1 over e, but e to the 1 over e is less than e. I think that's pretty clear because 1 over e is less than 1. But now let's observe that that means that x to the x is going to be less than e to the 1 over e raised to the e power, where I replace the base with e to the 1 over e, and I replace the exponent with e, because I've got this inequality right here. But now notice I can put those two things together and I just get e. So we've got x to the x is also less than e. But now let's observe that x to the x to the x is going to be less than e to the 1 over e to the x to the x. I guess it's less than or equal to that. But then x to the x is less than e. So this whole thing is less than e to the 1 over e to the e, but all of that is equal to e. And now I think you see an inductive path to show that the nth tetration of x is always going to be less than e. But that means we can put something bound above here of e. So that means that our sequence, which is this nth tetration of x, is increasing and bounded above. But then again, like I said, by the monotone sequence theorem, that means we know it converges. Okay, so that's good. We know that it converges on this most restrictive interval. Now we just have to determine if that's the entire interval of convergence, or if it's possible to have something less than 1 where this object converges. Okay, so let's look at that. Okay, so we just determined that if x is on this closed interval from 1 to e to the 1 over e, then our infinite tetration definitely converges. We use the monotone sequence theorem for that. Now we want to suppose that x is between 0 and 1 and see if we can get a condition on x so that this thing converges. Okay, so I'm going to start with a fact, and this is a fact of exponentiation for numbers that are between 0 and 1. And that is, if we have capital A less than capital B, then that implies that x to the capital B is less than x to the capital A. That's, of course, when x is between 0 and 1. So in other words, if you've got a number between 0 and 1, the exponentiation kind of gets reversed when you look at inequalities. I guess we could look at an example of this. So let's notice that 3 is most definitely less than 4. But if we take 1/2 cubed, that's going to give us 1/8, which is bigger than 1/16, which is equal to 1/2 to the 4th power. So just as an example of this kind of thing happening. Okay, great. But now I'd like to build off of this inequality and the fact that we've just observed over there. So let's observe that we now have 0 is less than x, which is less than x to the x, which is less than 1. And that's simply from applying the fact that x is less than 1 to our inequality over there. So we've got x to the 1 is going to be less than x to the x. Maybe we should write x to the 1 in there so we see that. And then we can extend this off. So let's also note the following, and I'm going to color code this so we can see where we're using our fact and our base inequality. So let's notice that x to the x to the x has got to be less than x to the x power. And again, that's just from the reversing behavior of our inequality when x is less than 1. So notice x to the x is bigger than x to the 1, but that means when we exponentiate it into this xth power, we reverse the inequality. So we've got this x to the x is less than x to the x. But now I'm going to add on the fact that this whole thing is less than 1, and then we can extend this out to see that x just to the first power is going to be less than x to the x to the x. And again, that's because 1 is bigger than x to the x. So that's just using that again. Okay, so let's maybe summarize that for just a second and notice that we have 0 is less than x, which is less than x to the x to the x, which is less than x to the x, which is less than 1. So notice that we've got these 1 and 3 appearances of x over here on the left-hand side, and then 2 and 0 appearances of x over there on the right-hand side. And this motivates a big inequality. And I'm not going to prove this, but you can prove this using the strategies that were just outlined here. And that is that 0 is less than x, which is less than the 3rd tetration of x, which is less than the 5th tetration of x, so on and so forth. Then we have an arbitrary odd tetration of x. But then all of the odd tetrations of x are going to be less than an arbitrary even tetration of x. So I'll just put less than ... here, less than an arbitrary even tetration of x. And then we can work down from that, the 4th tetration, the 2nd tetration, and then the 1st or the 0th tetration, which is just the number 1. So we've got this inequality right here. So let's observe that the odd tetrations are monotonically increasing and bound above by 1. The even tetrations are monotonically decreasing and bounded below by 0. So by the monotone sequence theorem, again, these two sequences individually converge. And in fact, we can say the following. The limit as n goes to infinity of the odd tetration, so the 2n plus 1st tetrations, converge to something that I'll call L sub odd, which is going to be less than or equal to L sub even, which is equal to the limit as n goes to infinity of the 2nth tetration of x. So that's what we gain from the monotone sequence theorem applied to this string of inequalities. Okay, so now let's see what we can get out of that. All right, so we built out these odd limits and this even limit, as well as the inequality between them, based off of this setup where x was between 0 and 1, and we looked at the odd tetrations and versus the even tetrations. Now I'd like to observe the following, that we've got the 2n plus first tetration of x is simply equal to x to the power of the 2nth tetration of x. But now we can take the limit of both sides of this, and we'll see that that means that L sub odd is equal to x to the power L sub even. And then via a similar analysis, we'll see that L sub even is equal to x to the power of L sub odd. But now what I'd like to do is solve both of those equations for x, and we'll see that L sub odd to the power 1 over L sub even is equal to x, but in turn, that's equal to L sub even to the power 1 over L sub odd. But now we can simply exponentiate by the product of L even and L odd, and that'll give us L sub odd to the power L sub odd is equal to L sub even to the power L sub even. Okay, cool. Now we've got two possibilities here. We have the possibility that L even and L odd are the same, in which case we do have convergence, or we have the possibility where they are different, in which case we don't have convergence. So let's determine where we don't have convergence. So let's assume that we have L odd is strictly less than L sub even. And then I want to consider the following function. And I'm going to call this function h of x, which is equal to, or maybe I'll call it h of t, which is equal to t to the t, just because I've already used x up there. And now, via a very, very similar analysis to what we did to t to the 1 over t, we can come up with a quick graph of this function. And what you'll see is that this has a minimum at 1 over e. And then it starts life out around the number 1, and that's going to be a limit as t approaches 0 from above. And then we'll get this minimum value at 1 over e. And then after that, well, since it's a minimum value, that means it has to like go back up. So the picture of the graph is something like this. So of course that's just a sketch, but that's the picture of the graph right here. But now, since L odd is less than L even, but then L odd to the L odd is equal to L even to the L even, we can see that L sub odd has to be over here to the left of 1 over e, and then L even has to be correspondingly to the right of 1 over e. So that tells us we have the following inequality. We have L sub odd is less than 1 over e, which is in turn less than this even limit. But now I can keep in mind that L sub odd, that odd limit, is going to be strictly bigger than x. So that gives us a range for x. Notice that x has to be less than 1 over e. So that means that we have divergence if x is less than 1 over e. But now let's see what happens if x is bigger than 1 over e. So let's observe that if x is bigger than 1 over e, well, we have the following inequality. So we've got 1 over e is less than or equal to x, which is less than L odd. But recall that L odd was less than L even implied that L odd was less than 1 over e. So L odd being bigger than 1 over e means that in fact L odd has to be equal to L even. So that means we get convergence if x is bigger than or equal to 1 over e. Okay, so we did a bunch of calculations. Now let's write down a summary of our discoveries. Okay, so now we're ready to look at a summary of our exploration for this problem over here. And that would be, well, an answer to our question. So x to the x to the x to the x to the x, so on and so forth. So this infinite tetration of x converges if and only if x is on this closed interval from 1 over e to the 1 over e. And that's a good place to stop.